said, we're going to do the other part of the lesson, basically showing you why do we want these Vy equations and where they're applicable, other than the fact that you could have used them for like the Bellwork problem. There's an easier way to go, right? And so why would we want to use these two equations? So I've included this slide to kind of just rehash what we talked about last class, although we kind of reviewed more with you guys since we took 2 days. But again, remember that the horizontal motion is always constant. The vertical motion is the same as something that's free falling. The reason why we see this parabolic path is because of the fact that we're superimposing two motions together. One's uniform motions and one is accelerated motion. So this is where I want to kind of use this slide to talk about the value of the Vy equations, right? Since the projectile is moving in 2 dimensions, it has 2 components, right? This idea of it has a Vx component and a Vy component, right? V is how fast it's really going, right? This is its real speed. This is the X component. That's how fast, right? It's moving in this horizontal direction. And you can see that this horizontal vector, remember this is a vector, right? A vector, we talked about that by using Despicable Me, right? He commits crime with magnitude and direction. So the length of this is supposed to give you an idea how big something is. In this case, this length they're showing you is representing 100 meters per second. And then the arrow tells you the direction. So this is Vx, right? As we've said, now Vx we know never changes. And you see that as the cannonball is shot, you see that it stays at 100 meters per second, right? So that's easy because it never changes. But what about the y? Well, we know when the cannonball is launched right here, right? Voy is equal to 0, right? Because he's launching it horizontally. But then we see it get bigger and bigger and bigger and bigger and bigger, right? And now they're giving you time. And so based on what they give you, right? So this is Vy, right? Is the down vector. It's increasing. It's increasing by an amount that we can calculate based off this equation, right? Again, we know this is 0. And this also kind of goes to some of the questions, like maybe one of the questions on each of the last tests, where it says, what if I double this? What happens to D or what happens to T, right? They're conceptual questions, but they're conceptual questions with a nod to using equations to help you figuring them out. And so this is one of those ideas. You see that as time increases by 1 second, the Vy value is increasing by 10 meters per second, right? And where that comes from is right here, because we know G is equal to 10. So it's 10 times 1, 10 times 2, 10 times 3, 10 times 4, all the way to 12, 10 times 12. When it gets right here, it's going 120 meters per second for Vy, right? So it's increasing by 10 meters per second every second. So now what that tells me is that Vy is directly proportional to time, right? So if we make time 10 times bigger, we're making Vy 10 times bigger. If we make time twice as big, Vy is going to be twice as big. They are directly related from this equation, right? And that's how you answer those questions when you get them and it says, you know, we launch the arrow with a velocity and it goes to a certain height d, but now we double the velocity, what happens to d, right? So then we would go to the other equation to see what are the factors and then figure out the relationship. In this case, we know that Vy is directly proportional to time, and it's going to increase by 10 meters per second every second. So that gives me what Vy is, right? And that's the value of the Vy equation. Now we have the other equation, but because this little animation goes based off time, if they had given us this value, right, where it's going to land, then we would use this equation and figure out based on distance, right, what is Vy? Now you see in this equation, Vy is squared, right? Again, we know that is equal to 0. So 0 squared is 0. And now we look at this equation, again, 2 is a constant, it's never going to change. Cannonball, right? G is a constant, it's 10, it's not going to change. And so what this tells me is that Vy squared right? Vy squared is proportional to dy, right? So if you double dy, Vy does not double, right? Because, and so you're looking at y is affected by x. And you can go the other way, right? Which we did for some of the, there was like one question, I think, on free fall and the projected upwards test where what if we double this? What happens to this? Well, if we double this, it is 2 squared or 4 times greater height. Well, what if we double this? Well, then it's the square root of 2 for Vy. And so you use, but this is not a linear relationship, right? And so that's how you kind of answer those questions. But we didn't need this equation for this idea because it was based off of time. But that's where we're going to use these equations. So Vx remains constant, right? Because there's no horizontal acceleration. But vertically, we have acceleration. It goes from 0 to 120 and accelerates at the rate of g, 10 meters per second every second. So we can use one of these two equations to find Vy. And it's going to be based on, in the problem, did you already solve for time or was this given? That's how you're going to decide which one's easier to use. Now, but what do we really want to solve for, right? And this is the new, kind of the new piece, is when it hits the ground right here, right? So you can see the values, Vx and Vy, but how fast is it really going, right? What I mean by that is, what is its final velocity, right? But before we started two-dimensional motion, we didn't have to worry about that because it was only moving in one direction. And we knew the velocity that was given was its final velocity. But now we're talking about this x and y velocity values. And when we get those individual values, that's not how fast it's really moving. It's not moving 100 meters per second and it's not moving 120 meters per second, but it's moving the combination of the two. So the question is, how do we find that final velocity? And that is where I don't remember the year and time that this came about, but Mr. Pythagorean or Pythagoreus, right? I think he's one of those guys that just has a first name with no, like Aristotle, like who knows what Aristotle's real name is. But because of him, we can figure this out because what we do is we take these vectors, these Vx and Vy vectors, and this is called vector addition. And so we used to spend a whole unit on this stuff, but we now kind of instead incorporate it into the units that we do teach. And so what I'm doing is I'm taking the Vx vector and the Vy vector and I'm adding them. This is called vector addition. You probably haven't seen this before, but maybe in one of your math classes, you've talked about vectors and scalars besides what we've talked about. But what we're trying to find, right, is the real velocity. And the real velocity is this value of v. That's how fast it's really going when it hits the ground. So we have to take into account its horizontal component and the vertical component. And we use Pythagorean's theorem to find its real velocity. So it's just taking it, so we use the Vy equation to find this value. And then we take it one step farther and use Pythagorean's theorem, which you guys have used many, many times. I'm sure that's not a big deal. Now, the last step to this, right? So the 4-letter word of trig, right? You guys have all, or you should have all had some level of trig by now. The only trig we need to know is sine, cosine, and tangent. That's it. Those are which has got to be the first thing you learned when you took trig, right? I can't think of something that's more basic in trig class than those 3 trig functions. And so what we use is sine, cosine, or tangent. Right now, though, if we need to calculate what we call this angle of impact, right? When that cannonball hits the ground, what I'm going to do is I'm going to calculate either this angle or this angle that it impacts the ground. Normally, we always usually measure our angle with respect to the horizontal. So that's the angle theta. Theta is our symbol, right? We can use theta and phi and alpha and beta, and I don't know what else you guys use in math class, but for physics, if we only have one angle, our go-to symbol is theta. So tangent of theta equals opposite over hypotenuse, or over adjacent, sorry, what I was thinking. Now, that doesn't mean you can use sine and cosine, right? Because sine of theta based on this triangle is opposites over hypotenuse, which is what I was originally saying, and cosine of theta is adjacent over hypotenuse. And so once you solve for v, you can use either of the trig functions. So if you look in a textbook or you look online and someone has a problem that's based off this, they're probably going to use tangent because that's kind of the go-to trig function to use for this. Now, if the problem only asks for speed, then we do not need to know this part. We don't need to do tangent of theta. But if it asks for velocity, right? Velocity is a vector and it requires direction, right? Where speed is a scalar and we don't care about the direction. So then we are definitely going to need to use something, in this case, one of the trig functions, to find what theta is. So whenever we do physics trig, we have to be in degrees. So you got to remember, if you're in radians from your math class, you got to switch it. And then when you have tangent theta, which I hope you guys know how to do this, so I'm just assuming you do, to get theta, right, we have to do, it's like if you have vx squared plus vy squared, to bring it to the other side, you do the opposite of adding, subtracting, opposite of multiplying is dividing. Well, the opposite of tangent theta is the inverse tangent. And so for most of your calculators, you're going to look for the second function and then hit tangent, right? Which will then, so you'll do this math, you'll have, well, it depends on calculator you use. You'll hit second function tangent and then whatever that decimal is, and then hit enter and it gives you the angle. And so then you would say, 140 meters per second at this angle is the angle of impact, right? But if it says speed, then we don't care about that. So that's why we would use those Vy equations. If the problem asks for the resultant, right? And think about the root word of resultant is result. So it's the answer. It's the real speed. It's how fast it's going. So let me show you an example, because I usually think after talking about the concept, sometimes if we apply it to an example, then maybe that helps hammer it home a little bit more. So I don't remember if I showed you this picture in one of the two classes or not, but I know I talked about with some of my classes already that back when I played video games, if I was playing like flying a plane and trying to bomb an enemy tank, or some of those really simplistic games they had back in the 80s, you would have to, if the tank was here, you would have to hit the space bar right above it, right? Because it's not correct physics. Now you guys have, such realistic games that you're going to actually, it's going to work properly for the most part. And so, but there's a misconception because of that, that if you were to throw this package out right here, that it would land right here. But it's not, because the package is also going the same speed horizontally, right, as the plane. And so it's going to land somewhere over here, right? And so while that Vx value is constant, the Vy value is constantly increasing because of gravity. So here's the problem that kind of goes with that. The plane is flying at 40 meters per second and it's 100 meters above the ground. These people are, some people stranded, some explorers, and they're going to drop it so that the whatever they're dropping to them, the package is going to land right there, right? Because we don't want them to have to walk miles to get their stuff. So what are the horizontal and vertical components of the velocity of the package just before it hits the ground, right? So obviously, I can't believe, usually this question would have been asked by now in the last unit. When we solve for the final velocity, people will be like, well, isn't the final velocity 0? Obviously it is when it hits the ground and stops. So we're always looking at that instant before it hits the ground, right? Right before it, because the whole idea of an impact is a completely different part of physics that we haven't reached yet. And then what is the speed of the package as it hits the ground? All right, so what do we know? Now, this is a problem that has other parts to it, like calculating what is dx. So I just kind of took away those parts to really just concentrate on what's new. So what do we know? We know that the plane is traveling 40 meters per second. So when they throw this package out, it's moving 40 meters per second horizontally. And we know that package is being dropped from 100 meters, right? Well, what else do we know? We know the initial vertical velocity. Normally planes fly horizontal, right? They get you up to the altitude, you stay horizontal. So that makes sense. Again, we know that the vertical acceleration is going to equal g. The horizontal acceleration is going to equal 0, right? We don't care about what dx is, but if the part A of this problem, we probably had to solve for dx, and so you would have probably solved for time. So it might have determined which equation for Vy you were going to use. But if this is our part A and this is part B, and this is the only parts of the question, we know that Vx is 40. It's not a trick question, even though it asks that, right? So you don't try to calculate something. You just, that's one of those things where like, all right, I understand the concept that the horizontal velocity doesn't change. And so the answer is 40. I don't have to calculate something else that doesn't exist. But for Vy, we've got to make a choice. And since I know this value and I don't know time, unless I want to solve for time, then I am going to use this equation because I don't know what time is currently. And so in order to get the time, I would have to calculate it. And so I'm not going to do that. Even though this equation has squares and the other one doesn't, I'm going to use this equation. And I'm going to solve for Vy because that is the vertical component of the package, right, when it hits the ground. So that is Vx. This is Vy. And so that's what I'm looking for. What is that value? We know that it starts out at 0, but it increases. So we know this is 0, right? So Vy squared. And this is what happens when some of you guys are losing, like right there when I wrote that, I almost didn't write it first before I wrote this. And I think that's what happens. You write this and then you forget to carry the square around. But we want Vy. So the next step is we are going to take the square root of both sides. Right, which gives me Vy. But now you got to remember when we take the square root, there's a plus or minus out there. Right, we've talked about that before. For us, plus and minus is direction only. And so because for me, if this is positive and up is positive, then I'm rejecting the positive because this is falling down and my Vy value has to be negative. Right, that's that point that some of you guys are missing. Because you're making like this negative, but then you're not making that negative, but you're getting an answer, which if you put it in your calculator with the negative signs, it would tell you that it's not possible, right? Basically, Vy, the acceleration, and dy should all have the same symbol, same sign for these problems, right? As long as we know for free fall, basically, is that is true. Obviously, it's not quite, sorry. I wonder if I use just the annotate. All right, so there's two ways I can write on these things. One is annotate, but it stays. So let me catch back up. And hopefully it doesn't do that with the annotating. Take the square root, take the square root. There's the plus or minus. We reject the positive, right? Because we want it down as negative. So we get back to this point right here. So now when I plug in my numbers, 2, -10, down is negative, -100. Why? Because it's falling 100 meters below, down is negative. These two negatives make a positive, and that mathematically will work out, right? So now I have square root of 2,000, which I think is 44.7. Let's see if my brain, yes, 44.72. So we'll round that to 44.7 meters per second. So that's Vy, that's Vx. Now we've answered part A. Part B, what is the speed of the package as it hits the ground? So for part B, we want to know, right, how fast is it really going? This is Vx, this is Vy, that's what we've calculated, but we want to know its real speed. What is V? And so what we do again is we make these these horizontal or these velocity vectors into a right triangle that looks like this, right? And you can go this way and just you'll have a different angle. You can do it either way. I always like to draw mine X to Y. Just for the reason why I do that is because later when we do things, we want the X component adjacent to the angle, so it's always cosine, and Y is opposite the angle, so it's always sine. So it just kind of helps if you're not great at trig or you get confused with trig, it makes some of those, takes out some of the guesswork, so to speak. And so for part B, we need to use Pythagorean's theorem, right? And we want V, so we're just going to take the square root of both sides, right? So now plug in your numbers. You have 40 squared. We don't need to put the negative sign in because it's going to get squared anyway, right? And we know speed doesn't have direction, so it can't be negative. So I don't need to put in a plus or minus out here because, again, it says speed, right? And there's no negative numbers on your speedometer in your car. So now if I do this, oops, square 44.7, add 40 squared, you get 60. How about that? Square root of 3,600, perfect. 60 meters per second. That's my answer. That's how fast it's really going when it hits the ground, right? But these values of 40 and 44.7 are the components, right? They make up that value of 60. Now, it doesn't ask for this, but just as a quick review of trig, if it asked for the velocity, we would just do this one extra step, right? Then I would include, so I would make, if it was velocity, I would include the negative sign because it's down, right? But I would take Vy over Vx, opposite over adjacent, do the inverse tangent, make sure your calculator is in degrees, right? So it'd be the inverse tangent of 44.7 over 40. And so depending on if you have a TI or a Casio, it may be a little bit different. But for me, I hit second tangent. So it says tan -1. I put in 44.7 divided by 40, close the parentheses, and I get 48.176, right? 48.2 degrees. Right, so it's that horizontal. That would be the velocity answer, right? The speed answer, you'd be done right here. You would just do this extra step to get the velocity. These are the kinds of problems where you're going to use the Vy equation to find the final velocity. And so on your homework for next Tuesday, there's a couple of those problems instead of what we had the basic problem for today. Questions?
Just double checking, this entire lesson will be at Doc After Dark.
Yeah, it would be either there or it'll be in our Canvas, one or the other. And then once I figure out how to give you the link for it, I'll put that there. All right. So the problem is with annotating is to go to the next page and not see all that work I have to clear. So it has to go. That's the problem with annotating compared to the other method that's down here. All right. So what I want you guys to do, this is the computer simulation. So I'm also going to stop recording because